Okay, question 4. A toy is used to launch the ball. So we've got a spring here. So we know that this is going to store some elastic potential energy. We're going to have to apply a force on the handle to put that elastic potential energy in. So that person will be using some chemical energy. And then eventually they're going to let go of it, and that's going to project the ball forwards and give it some kinetic energy. So the child pulls the handle, stretching the spring. So let's just do that there. So that's the child. Which of these shows the forces acting on the handle when the child keeps the spring stretched? So what do we know? We're going to have the force of the child going that way, and then we're going to have a force within the spring because we've stretched it and stored some energy in it. Here, so I'll put force child, force spring. What do we know? Well, if it's not moving and it's just waiting to be launched, we know that these must be equal in size and opposite in direction. So we're now looking for a pair of arrows that are equal in size. Not you, not you, not you, and opposite in direction. Perfect. D. On to the next one. So now we're going to need our Kentucky Fried X-rays. So Kentucky Fried X-rays, and it tells us that the spring constant is 20 newtons per meter, so we've got that. The extension is in meters, no unit change, beautiful, and it wants to know the force, F. So we just got to multiply those two things together. So F equals K times X, take the 20 for the spring constant, times by 0.070 equals 1.4 newtons, done. The next one, the extension of the spring is 0.09 meters. Great, no unit change. Gives us the spring constant is 20 newtons per meter. Calculate the work done. So the work done is the elastic potential energy stored. So it gives us an equation. So half, which we would put in a calculator, is 0.5 times 20 times, because we know EPE equals half kx squared, and that's the bit that's going to get missed. They're going to miss that little squared there, times 0.09 squared. So you put that all into your calculator and you would get 0.081 joules. But just please remember that squaring. The child lets go of the handle, the ball starts to move, and the spring returns to its original length. So we have a coiled up spring, and then boingy, 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 and it's going to launch the ball out. Describe the energy transfers that take place when the ball starts to move. So again, we're going to start talking about the EPE transfer into kinetic energy. So the elastic potential energy stores will transfer to kinetic energy stores, and then as this moves through the air, some of these kinetic energy stores, we're going to have air resistance. This is a frictional force, and that's going to create some heat. So we've got in terms of my diagram, I'm then going to say I'm going to talk about EPE to KE to thermal energy due to friction in the air. And when that ball hits the floor, we'll then have some more thermal energy transferred into the floor. On to the next one. The child can only stretch the spring until the pad is pressing against the support. So what do we know? So we're saying here's the support. We're pulling that spring in. And we got a limit because we can only put these coils so close together. There's no more space for the coils to go together. So this toy has a limit in terms of how much elastic potential energy we can store. And the limit is how much can we squash this spring inwards. So explain how the design of the toy prevents the spring from becoming damaged. So the crucial part is, well, the reason I'm compressing this spring rather than stretching the spring, if we're to stretch something, we've learnt that it obeys Hooke's law for the first part, and then we get to something called the elastic limit. So if I go, let's have that as the force, and let's have that as the extension. We get to a point, so in this part here, it obeys Hooke's law. As I stretch you, you'll go back to your original shape, but then we reach the elastic limit, and it no longer obeys Hooke's law. And here, the spring won't go back to its original shape, it'll stay deformed. So the crucial part is, why are we squashing it? We're squashing it so that it never reaches this elastic limit. So this prevents the spring being stretched past the elastic limit, 1 mark. So the point at which it'll no longer go back to its original shape. And then we're just going to state what happens. So, whoops, as the spring would no longer go back to its original shape. So that's the design. So the whole design of squashing a spring rather than stretching it is so it keeps going back to its shape, so your toy works. You'd be a bit miffed if your toy stopped working after the first chuck of a ball at your mate. Done.